This is the second video in our SLO8. It's actually the second part of SLO8A, right? Confidence intervals for a population mean where the standard deviation is known. So we're just going to continue doing confidence interval examples, right? Remember, we're using confidence intervals to estimate the population mean. Given a simple random sample, size n, from a population whose standard deviation sigma is somehow known. Again, this is a little bit unrealistic. Now, remember, we're making a couple of assumptions. The sample has to be random, otherwise it doesn't work. And either the sample is large, meaning n is greater than 30, or the population is approximately normally distributed. Also, remember the formula for the confidence interval is, again, I'm getting a little technical with the notation here, 1 minus alpha CI equals your point estimate minus your margin of error. So the point estimate plus your margin of error. And then this is the same thing as the point estimate minus our z-score. Right, that's sort of specialized z-score times our standard error. And then our point estimate plus that same value right there. That's what it is. I can move this down. Now, this is a nice little picture that they have from the book. So I encourage you to read this section and understand where they're coming from here, although I do have the caption. Now, remember that the confidence level of our interval affects the length of our interval. Higher confidence level means a longer interval, right? We're more confident that the true population mean is going to be within our interval. But our interval is longer, so we have a wider range of values, so it's not quite as helpful as a shorter interval. Right, we want to try to narrow it down as much as we can, while at the same time being reasonably confident. So there's that, right? You can pause the video and read the caption if you'd like. Let's look at example 1 really quickly. Here we've got a sample of size 10, kind of a small sample, but the population is normal, so we're okay. Right, we've got the population standard deviation, we've got our point estimate, 95% confidence interval. This should not be too bad, right? We're just using Minitab here. Stat, basic stats, right? We had a sample size of only 10. Sample mean 7.92, and then that. I think that was the standard deviation. And I think they wanted a 95% confidence interval. Right? So that's what we've got. 6.371 to 9.469. Let me just do that real quick. So I'm just going to be lazy, not even write it, just put the Minitab. Right, there, let's try to get a better circle. There, okay. Now, if the population were not approximately normal, would this be valid? No, because our sample size, n is less than, right, it equals 10, which is less than 30. I guess I should say less than or equal to 30. We need n greater than 30 to guarantee an approximately normal sampling distribution. Right? And that's what allows us to do all of this confidence interval, z-score, standard error stuff, right? We need our sampling distribution to be normal or approximately normal. So we need either our population to come from a our sample to come from a normal population, or for our sample to be large enough. Okay. Now, we've seen that we can decrease the margin of error by, well, what can we do? We can just decreasing our confidence level, right? But this increases the likelihood of the population mean being outside our interval, which means that we use statistics to get an inaccurate estimate, which is really not a good thing. It's going to happen sometimes, but we don't want it to happen too often. Okay. The other way to decrease the margin of error is to increase the sample size n, right? And that's because the standard error right, sigma over root n decreases as n increases, right? Think about the denominator of this fraction. Denominator gets bigger, fraction gets smaller, right? So if you redo example 1 for sample size n equals 20, look at the length of the confidence interval. Right? Basic stats, one sample z, and let's make this 20 instead. Okay, we get another confidence interval. I will screenshot this, and we'll compare it side by side with the one we previously got. Right? We're just going to see the lengths of the intervals. Right, so this was n equals 10. And this is n equals 20. Right, and just note the length of the confidence interval here, right? For 10, we have this length. For 20, we have this length, right? Note that this second interval is shorter, right? The green interval is shorter than the yellow interval, right? Because we just have more data. So the one thing you could say is we could tailor n to reach a precise margin of error, right? Suppose we want a 95% confidence interval. How many individuals do we need to sample for the margin of error to equal 1? Right? Well, you can guess and check, right? We know, i.e., we need our confidence interval to be, I guess I should say our 95% confidence interval to be 6.92 to 8.92. Or smaller. Right? Now, one way you could do this is you could just guess and check, right? We go back into Minitab, right? We say 6.824. Oh, that's not as good as 6.92, right? So we as 6.92, 8.92, right? So we go back in here and say, maybe instead of 20, we could try 23. And then, oh, that's close, but not quite. Maybe we could try a little bit more and do 24. And, oh, that's so close. Actually, that looks like it got it for us. 6.920, so maybe it's 24. if we just try one more time, right, if we go to 25, right, because I think there might be some rounding at play. Nope, yeah, so I guess it really is 24. It looks like it's 24, I should say. Using Minitab and guessing and checking, it looks like we need n to equal 24 individuals sampled, okay? But that's not ideal. Guessing and checking is never ideal. It'd be better if we had a formula, right? So it turns out we do have a formula. Let me show you how we get it, and then I'll write the formula down, right? We know that the margin of error equals our z-score times sigma over root n. Yeah, let's get rid of the alpha over 2. I don't want to confuse anyone, right? So if we solve for n, so what we're going to have is I'm going to multiply both sides by the square root of n. And then I'm going to divide both sides by the margin of error. But I don't want to solve for the square root of n. I want to solve for n. So I'm going to square both sides. So I get that n equals all of this stuff squared. Okay? And really, what we need is we really want n to be greater than or equal to this, right? Because we need the margin of error to be at least that. So let's see. If we go back and do it, so right, that's our formula. And actually, I guess I can do, yeah, this should be greater than or equal to. Right, so we can say greater than or equal to, greater than or equal to. Okay. All right, so anyway, that's our formula, right? It's going to be n greater than or equal to z times sigma over the margin of error, quantity squared. So here, if we go back and use the formula, what are we going to get? We're going to get that n needs to be greater than or equal to our z value times sigma divided by the margin of error, quantity squared. Well, let's see. We know that our margin of error is going to be 1, right? That's our desired margin of error. Okay, and then what was our z-score? Well, we're looking at example 1. We wanted a, what was that, 95% confidence interval? Well, if we remember, I think that z-score was 1.96. And our sigma was that 2.5? Yeah. All right, and then if you do this out, I'm pretty sure it's going to give you about 24.01, right? Let's do this out, right? 1.96 times 2.5. And now we're going to square this. $24.01, okay? But here's the thing. We need it to be bigger than 24.01, right? Greater than or equal to 24. We don't have 0.01 individuals. So n needs to equal or be greater than or equal to 25, right? So just showing you that guessing and checking is not always the best approach, right? Didn't really give us what we wanted. All right? Now, one more example just to close things out. All right, let's see. We've got a sample of 75 clamps. Mean time is 50.1. Standard deviation sigma, 95% confidence interval, right? Should not be so bad. Again, Minitab, use the data, right? N equals 75. Mean equals 50.1. Sorry, I actually forgot all of it. Yep, N equals 75, 50.1. And the standard deviation was 10. And they want a 95% confidence interval. Looks like we're set at that. And so that's our answer. Oh no. We did not want that. I apologize for that. We wanted that. There we go. There's our confidence interval. All right, and then secondly, find the sample size needed so that a 98% confidence interval would have a margin of error 1.5. So a 98% confidence interval, well, I'm not exactly sure what the margin, what the z-score would be for that. So if I go in to Minitab, graph, probability distribution plot, right? And we go here, do specified probability, middle, I'm going to do 0.01. What? No, 0.01. Right? Because that's the remaining area on either side of 0.98. So it looks like it's 2.326. Right? So for B, 98% leads to Z equaling 2.326. Did I get that right? Do I remember that correctly? Yes, I do. Okay. Right. So N needs to be greater than or equal to, and we're just using the formula, right? Remember, it's Z times sigma over the margin of error squared. So this is going to be 2.326 times our standard deviation, which is 10, over 1.5 quantity squared, which is going to equal 23.26 over 1.5 quantity squared. Let's see. 240 and change. Right? So we need N greater than or equal to 241. And that's all for today.